Could this drop power every home on Earth? Welcome to Fusion Unchained, where we journey from that single seawater droplet to the blazing cores of Tokamak reactors. In the next hour, you'll discover how AI-driven insights are mastering star-like plasmas, how magnetic rings recreate fusion's fire, and what it means for a zero-emission, limitless energy future. Recent breakthroughs have brought this dream closer to reality, igniting a global race to harness the process that fuels the sun. Join us as we delve into the science, challenges, and extraordinary potential of fusion. From the moment our ancestors first kindled fire, humanity has been on an unyielding quest for energy. It fuels our homes, drives our industries, and connects us across continents. Yet our dependence on fossil fuels has come at a steep price. A warming planet, polluted skies, and geopolitical tensions fueled by competition for finite resources. The need for a clean, sustainable, and abundant energy source has never been greater. Renewable sources like solar and wind offer a vital part of the solution, but they are inherently intermittent, reliant on the whims of nature. Fusion, on the other hand, holds the promise of a baseload power source, one that can provide a constant and reliable stream of energy, day and night, rain or shine. But fusion is not just about replacing old energy sources, it's about transforming our relationship with energy itself. Imagine a world where energy poverty is eradicated, where developing nations can leapfrog outdated infrastructure and embrace a future of sustainable growth. Imagine a world where the energy that powers our lives is as clean and limitless as the sun itself. This is the transformative potential of fusion. The key to unlocking fusion's potential lies in an unexpected place, the vast shimmering expanse of our oceans. Seawater, often taken for granted, holds the essential ingredient for fusion deuterium. This naturally occurring isotope of hydrogen, found in abundance in seawater, is one of the two primary fuels for fusion reactions. A single cubic meter of seawater contains enough deuterium to generate the energy equivalent of over 300 litres of gasoline. To put that into perspective, the Earth's oceans contain enough deuterium to power human civilization for millions, if not billions of years. The other fuel for fusion, tritium, can be produced during the fusion process itself, using lithium, another readily available element. This means that fusion reactors, unlike their fission counterparts, do not produce long-lived radioactive waste. The primary byproduct of fusion is helium, an inert and even beneficial gas. Fusion, at its core, is the process of fusing together light atomic nuclei to release enormous amounts of energy. It is the same process that powers the sun and other stars, bathing our solar system in light and warmth. Replicating this stellar process on Earth, however, is a feat of immense scientific and engineering complexity. Fusion requires unimaginable temperatures and pressures, millions of degrees Celsius, hotter than the core of the sun itself. To achieve these extreme conditions, scientists are pursuing several approaches, the most promising of which involves confining a superheated plasma, a swirling cloud of electrically charged gas, within powerful magnetic fields. Imagine a miniature star held in check not by gravity but by invisible magnetic forces swirling and churning within a specially designed reactor. This is the essence of magnetic confinement fusion, the approach that has garnered the most attention and investment worldwide. The fusion frontier. The quest to achieve practical fusion power is a global endeavour. with research institutions, private companies and governments around the world pouring resources and expertise into overcoming the remaining technical hurdles. The field is buzzing with excitement, driven by a potent mix of scientific curiosity, technological ambition, and the sheer scale of the potential rewards. Giant experimental reactors such as the International Thermonuclear Experimental Reactor in France are pushing the boundaries of fusion science, seeking to demonstrate the feasibility of net energy gain, the holy grail of fusion research. Meanwhile, smaller, more agile startups are exploring innovative approaches that could accelerate the timeline to commercial fusion power. The race to fusion is on, and the stakes could not be higher. It is a race not just for technological supremacy, but for the future of our planet and the well-being of generations to come. The heart of the matter. To grasp the sheer audacity of fusion power, we must first journey into the heart of matter itself, to the realm of atoms and the forces that bind them. Atoms, the fundamental building blocks of everything we see and touch, consist of a dense nucleus orbited by even tinier particles called electrons. It is within the atom's nucleus, a space far smaller than the atom itself, that the extraordinary energy of fusion resides. The nucleus is composed of protons, which carry a positive charge, and neutrons, which have no charge. These particles are held together by the strong nuclear force, one of the four fundamental forces in the universe. The strong force is incredibly powerful at short distances, overcoming the electrostatic repulsion between the positively charged protons and binding the nucleus together. It is this binding energy, the energy that holds the nucleus intact, that is released in a fusion reaction. The dance of atoms. Fusion occurs when two light atomic nuclei, such as those of deuterium and tritium, overcome their natural electrostatic repulsion and collide with enough energy to fuse together. This fusion creates a heavier nucleus, typically helium, and releases a tremendous amount of energy in the process. Imagine two tiny magnets, their north poles facing each other, repelling each other with invisible force. To overcome this repulsion and force the magnets to touch, you would need to push them together with immense force. Similarly, to achieve fusion, we need to overcome the electrostatic repulsion between the positively charged nuclei. This requires heating the fuel to extremely high temperatures, tens of millions of degrees Celsius, so that the nuclei are moving fast enough to overcome their mutual repulsion and collide with sufficient force to fuse. At such extreme temperatures, the fuel no longer exists as a gas, but as a plasma, a swirling sea of electrically charged particles, often referred to as the fourth state of matter. Containing and controlling this superheated plasma is one of the most formidable challenges in fusion research. Imagine trying to hold the sun itself in your hands. The plasma, hotter than the sun's core, would instantly vaporize any material it touched. To confine this inferno, scientists have turned to an elegant solution: magnetic fields. Just as iron filings align themselves along the invisible lines of force around a magnet, charged particles in a plasma can be confined and controlled by magnetic fields. By carefully shaping and manipulating these magnetic fields, scientists can trap the plasma, suspending it within a vacuum chamber and preventing it from coming into contact with the reactor walls. Several different magnetic confinement concepts are being pursued worldwide, each with its own advantages and challenges. The most advanced approach, and the one that underpins ITER, is the Tokamak. The Tokamak, a Russian acronym for toroidal chamber with magnetic coils, uses a combination of magnetic fields to confine the plasma in a donut-shaped chamber, or torus. The plasma is heated to fusion temperatures by a combination of methods, including powerful radio waves and beams of high-energy particles. Maintaining the stability and temperature of the plasma within a tokamak is a delicate balancing act, requiring sophisticated control systems and a deep understanding of plasma physics. The plasma is inherently unstable, prone to turbulence and disruptions that can cool it down or even extinguish it altogether. The ultimate goal of fusion research is to achieve ignition, the point at which the fusion reactions within the plasma generate enough energy to sustain themselves without the need for external heating. At this point, the fusion reactor becomes a self-sustaining power source, releasing more energy than it consumes. Imagine lighting a match to a pile of wood. Initially, you need to provide the heat to ignite the wood, but once the fire catches, it generates enough heat to keep itself burning. Similarly, achieving ignition in a fusion reactor would mark a pivotal milestone, demonstrating the feasibility of fusion power and paving the way for commercial fusion power plants. The quest for fusion ignition has brought together nations in an unprecedented collaboration. The International Thermonuclear Experimental Reactor, or ITER, currently under construction in southern France, is one of the most ambitious and complex scientific projects ever undertaken. ITER, a collaboration between 35 nations, represents the culmination of decades of fusion research and international cooperation. The project aims to demonstrate the scientific and technological feasibility of fusion power by building and operating the world's largest and most advanced Tokamak fusion reactor. ITER is a testament to the shared belief in the transformative potential of fusion energy. It is a beacon of hope in a world grappling with climate change and energy security, a symbol of what humanity can achieve when we work together towards a common goal. The allure of fusion power extends far beyond its sheer energy potential. It is, at its core, a clean energy source, promising a future free from the environmental burdens that have plagued our reliance on fossil fuels. Imagine a world where the air is clear, the skies are blue, and the threat of climate change recedes with each passing year. Unlike coal-fired power plants, which spew harmful pollutants into the atmosphere, fusion reactors produce no greenhouse gases during operation. The primary byproduct of fusion is helium, an inert and even beneficial gas used in medical imaging, scientific research, and even party balloons. This inherent cleanliness extends beyond the absence of air pollution. Fusion reactors do not produce long-lived radioactive waste, the disposal of which has been a major concern with conventional nuclear power. While some components of a fusion reactor would become radioactive during operation, these materials have much shorter half-lives than those produced in fission reactors, significantly reducing the challenge of long-term waste management. The waste management aspect of fusion power deserves special attention. Unlike fission reactors, which generate hazardous waste products that require careful containment and disposal for centuries, fusion reactors produce minimal waste, and what they do produce decays to safe levels relatively quickly. The primary waste product, as we've mentioned, is helium, an inert gas. There would be some radioactive waste generated from the materials used in the reactor itself, but the volume would be far less than that produced by fission reactors, and the radioactivity would decay much faster, typically within decades rather than millennia. This dramatic reduction in radioactive waste significantly diminishes the long-term environmental impact of fusion power. It also eases concerns about nuclear proliferation, as the materials used in fusion reactors are not directly suitable for weapons production. Fusion, therefore, offers a pathway to a cleaner, safer and more secure energy future. The fuel for fusion power is as abundant as it is unexpected: seawater. Deuterium, one of the two isotopes of hydrogen needed for fusion, is found in plentiful supply in seawater. The sheer volume of water in our oceans represents a virtually inexhaustible source of fusion fuel, enough to power human civilization for millions, if not billions, of years. To put this into perspective, imagine a world where energy scarcity is a distant memory, where nations no longer compete for control of dwindling oil reserves or struggle to secure access to natural gas pipelines. Fusion has the potential to reshape geopolitics, fostering collaboration over competition and ushering in an era of global energy security. The other fuel for fusion, tritium, can be produced during the fusion process itself using lithium, a readily available element found in various minerals and even seawater itself. This closed-loop fuel cycle further enhances the sustainability of fusion power, minimizing our reliance on external fuel sources and reducing the environmental impact associated with fuel extraction and transportation. The advent of fusion power holds particular promise for developing nations, many of which face significant energy challenges. Access to reliable and affordable energy is essential for economic development, improving living standards and lifting communities out of poverty. Fusion, with its potential to provide clean, safe and abundant energy, could be a game-changer for developing countries. Imagine a world where remote villages in Africa or Asia, currently lacking access to electricity, can power homes, schools and hospitals with clean energy from a nearby fusion power plant. Imagine a future where developing nations can leapfrog outdated and polluting energy infrastructure, embracing a sustainable path to economic growth and prosperity. Fusion has the potential to level the playing field, providing all nations, regardless of their size or current stage of development, with equal access to the energy resources they need to thrive. It is a vision of a future where energy poverty is eradicated and the benefits of clean energy are shared by all humankind. The applications of fusion power extend far beyond simply generating electricity. The intense heat produced in a fusion reactor could be used for a variety of industrial processes, such as producing hydrogen fuel, desalinating seawater, and even recycling waste materials. Imagine a world where the energy from fusion powers vast desalination plants, turning salt water into fresh water and transforming arid regions into fertile farmland. Imagine industries powered by clean fusion energy, producing goods with a minimal environmental footprint. Fusion could also play a pivotal role in space exploration, providing a compact and powerful energy source for spacecraft, enabling longer missions and more ambitious journeys to the outer reaches of our solar system. The same technology that could power our cities could one day propel us to the stars. The pursuit of fusion power is not just about building a new energy source, it's about pushing the boundaries of human ingenuity and driving innovation across a wide range of scientific and technological fields. The challenges inherent in fusion research have already led to breakthroughs in plasma physics, materials science, supercomputing, and many other areas. Imagine a world where the quest for fusion energy ignites a new era of scientific discovery and technological advancement. The knowledge and technologies developed in the pursuit of fusion will have far-reaching applications, benefiting fields as diverse as medicine, computing, and materials science. Fusion has the potential to be a catalyst for innovation, inspiring new generations of scientists, engineers and entrepreneurs to tackle some of the world's most pressing challenges. It is a testament to the power of human ingenuity and our unwavering belief in the possibility of a brighter future. The pursuit of fusion power is a global endeavor, uniting scientists worldwide. Researchers collaborate across continents, pushing the boundaries of plasma physics and engineering. This effort is driven by the pursuit of clean energy and the desire to explore the unknown. From Europe to Asia, North America to Australia, fusion research is a global tapestry. Each experiment and breakthrough brings us closer to harnessing the energy of the stars. At the heart of the fusion endeavor lies a singular, audacious goal: achieving ignition. Ignition, in the context of fusion, refers to the point at which the fusion reactions within a plasma become self-sustaining, generating enough energy to maintain the plasma's temperature without the need for external heating. It is the moment when the dream of controlled fusion power transforms from tantalizing possibility to tangible reality. Imagine a campfire, the flames dancing and crackling, radiating warmth. Initially, you need kindling and careful tending to get the fire going, but once it catches, the heat it generates is enough to keep it burning, consuming fuel and releasing energy in a self-sustaining cycle. Ignition in a fusion reactor would mark a similar turning point. It would demonstrate that we can replicate and control the very process that powers the sun, unleashing a virtually limitless source of clean energy. Achieving ignition is not just a scientific milestone. It is a symbolic threshold, a testament to human ingenuity and our ability to harness the fundamental forces of nature. In the south of France, amidst the rolling hills of Provence, a sun is under construction. ITER, the International Thermonuclear Experimental Reactor, is a sun of magnetic fields and superheated plasma. This colossal scientific endeavor represents decades of fusion research and international cooperation. ITER is a cathedral of science, a monument to human ambition. Scientists aim to create a plasma hotter than the sun's core, confined by powerful magnetic fields. While ITER represents the largest and most ambitious fusion project to date, it is not the only game in town. Across the globe, researchers are pursuing a variety of complementary approaches to fusion, each with its own advantages and challenges. These diverse efforts reflect the dynamic nature of fusion research, a field characterized by constant innovation and a willingness to explore unconventional paths. Some groups are focusing on magnetic confinement fusion, like ITR, but exploring alternative reactor designs such as spherical Tokamaks or stellarators, which offer potential advantages in terms of plasma stability and efficiency. Others are pursuing inertial confinement fusion, using lasers or particle beams to compress and heat tiny pellets of fusion fuel, creating miniature explosions that release bursts of energy. This diversity of approaches is a strength of the fusion field, fostering a spirit of healthy competition and cross-pollination of ideas. Each approach brings its own unique insights and challenges, and the knowledge gained from these parallel efforts ultimately benefits the entire field, accelerating progress towards the shared goal of practical fusion power. The pursuit of fusion power has seen a rise in private investment and public interest. Startups fueled by venture capital bring fresh perspectives and urgency. Private investment signals belief in fusion's commercial viability. Investors see fusion's potential to revolutionize energy. Private funding accelerates progress and innovation. Fusion captivates the public imagination. Documentaries and articles spread fusion's excitement. Public awareness builds support for fusion research and projects like Reactor. The path from experimental fusion reactions to the electrification of our homes and cities is long and challenging, filled with technical hurdles and unforeseen obstacles. Yet, despite the challenges, there is a palpable sense of optimism within the fusion community, a growing belief that we are on the cusp of a new energy era. The pieces are falling into place. Scientific understanding of plasma physics is advancing rapidly. New materials capable of withstanding the extreme conditions within a fusion reactor are being developed. Advanced manufacturing techniques are making it possible to build the complex and precise components required for these sophisticated machines. The dream of fusion power, once relegated to the realm of science fiction, is now within the grasp of human ingenuity. The coming decades will be a pivotal time for fusion. A time of accelerated progress, groundbreaking discoveries, and ultimately the realization of a clean energy future, powered by the same forces that illuminate the stars. The journey from experimentation to electrification is well underway, and the destination, though still distant, shines brightly on the horizon. The allure of fusion, promising limitless clean energy, has beckoned scientists for decades. Yet, fusion's secrets are guarded by formidable technical challenges. Plasma, the superheated gas fueling fusion, is inherently fickle. Imagine containing a miniature sun within a magnetic bottle. The plasma writhes with unimaginable energy, seeking to escape. Maintaining stability is like balancing a feather on a hurricane's breath. The smallest imperfection can trigger instabilities, cooling the plasma or damaging the reactor. Overcoming these instabilities is a formidable hurdle to practical fusion power. The extreme temperatures required for fusion pose another daunting challenge. To force atomic nuclei to overcome their electrostatic repulsion and fuse together, we need to heat them to tens of millions of degrees Celsius, hotter than the core of the Sun. This intense heat places extraordinary demands on the materials used to build a fusion reactor, pushing them to the very limits of their physical properties. Imagine a crucible hotter than any furnace ever built, a place where even the most resilient materials begin to soften and glow. The reactor walls, bombarded by high-energy particles and bathed in intense radiation, must withstand these punishing conditions for extended periods without degrading or failing. Developing materials that can withstand this relentless thermal assault is a monumental task, requiring breakthroughs in materials science and engineering. These materials must not only be able to handle the heat but also resist damage from radiation, maintain their structural integrity under intense magnetic fields, and minimize contamination of the plasma, which can quench the fusion reaction. Materials under bombardment. The inside of a fusion reactor is a chaotic and unforgiving environment. High-energy neutrons, a byproduct of the fusion reaction itself, stream out of the plasma, bombarding the surrounding materials with relentless energy. This neutron bombardment can cause significant damage to the reactor's internal components, altering their structure, weakening their properties, and creating radioactive waste. Imagine a sandblaster, but instead of sand, it's a stream of subatomic particles traveling at incredible speeds. This constant bombardment can erode the reactor walls, create microscopic defects in the materials, and even transmute elements, transforming stable isotopes into radioactive ones. Mitigating the effects of neutron damage is crucial for the longevity and efficiency of a fusion reactor. Scientists and engineers are exploring a variety of strategies, including developing new materials with enhanced radiation resistance, designing clever shielding systems to protect critical components, and devising innovative maintenance strategies to repair or replace damaged parts. Taming turbulence. The plasma within a fusion reactor is not a placid sea of energy, but a turbulent and chaotic entity prone to unpredictable fluctuations and disruptions. These instabilities, often triggered by subtle interactions between the plasma and the confining magnetic fields, can wreak havoc within the reactor, leading to energy loss, reduced performance, and even complete loss of confinement. Imagine a pot of boiling water, the surface churning and bubbling unpredictably. The plasma within a fusion reactor exhibits similar chaotic behavior, with swirling eddies and sudden bursts of activity that can disrupt the delicate balance required for sustained fusion. Understanding and controlling this plasma turbulence is essential for achieving the stable and efficient operation of a fusion reactor. Scientists are employing advanced diagnostics and sophisticated computer simulations to study the complex behavior of plasma, unraveling the mechanisms that drive turbulence and developing strategies to mitigate its effects. The economics of fusion. The pursuit of fusion power is not just a scientific and technological endeavor, it is also an economic one. Building and operating a fusion power plant is an expensive proposition, requiring significant upfront investment and ongoing operational costs. Ensuring that fusion can compete economically with other energy sources is a critical factor in its eventual deployment. Imagine a balance scale, with the cost of fusion power on one side and the cost of alternative energy sources on the other. For fusion to tip the scales in its favor, it needs to demonstrate not only its environmental benefits, but also its economic viability. Several factors influence the economics of fusion, including the cost of building and maintaining the reactor, the efficiency of the fusion process, and the cost of fuel. Researchers are working diligently to optimize reactor designs, improve plasma confinement, and develop more cost-effective manufacturing processes to make fusion power more competitive. Fusion's intermediary steps. While the ultimate goal of fusion research is to achieve net energy gain and pave the way for commercial fusion power plants, the journey towards that goal is not a linear one. Along the way, there are numerous intermediary steps, each with its own set of challenges and potential benefits that can contribute to the advancement of fusion technology and its eventual deployment. Imagine a staircase leading up to a rooftop with a breathtaking view. Each step represents a milestone in fusion research, a stepping stone towards the ultimate goal of practical fusion power. These intermediary steps include achieving and sustaining higher plasma temperatures and densities, extending the duration of fusion reactions, developing more efficient and cost-effective reactor designs, and exploring alternative fusion concepts that could offer practical advantages. Each step along the way brings us closer to the realization of fusion's immense potential, and the knowledge and technologies developed along the way will have far-reaching benefits in other fields, from materials science to astrophysics. A world transformed. Imagine stepping out into a world utterly transformed. The air, once heavy with exhaust, is now fresh and clean. The skies shimmer with vibrant blue, the sun's rays unimpeded. This is the promise of a world powered by fusion. Cities are now havens of quiet efficiency. High-speed electric trains whisk travelers effortlessly. The air is alive with birdsong and children's laughter. The transformation extends beyond our cities. Deserts, once barren, are now blooming with life. These oases provide food and restore balance to ecosystems. The geopolitics of abundance. The geopolitical landscape, once carved up by competition for scarce resources, has been redrawn. Wars fought over oil fields and gas pipelines are a distant memory, relics of a bygone era when energy was a zero-sum game. Fusion's abundance has ushered in an age of cooperation, as nations recognize that access to clean, limitless energy is no longer a matter of national security, but a shared human right. International collaboration, once a fragile and often fleeting ideal, is now the norm. Scientists and engineers from around the world work shoulder to shoulder at fusion research facilities, driven by a shared desire to unlock the secrets of the atom for the benefit of all humankind. The knowledge and technologies developed through these collaborative efforts are shared freely, accelerating progress and fostering a spirit of global unity. The economic disparities that once divided the developed and developing world are beginning to fade. Access to abundant, affordable energy has unleashed a wave of economic growth and prosperity across the globe, lifting millions out of poverty and creating new opportunities in even the most remote corners of the planet. Perhaps the most profound impact of fusion is its potential to reverse the devastating effects of climate change. With fusion power replacing fossil fuels as the primary energy source, greenhouse gas emissions have plummeted, allowing the planet to begin healing from decades of environmental damage. The polar ice caps, once shrinking at an alarming rate, are slowly but steadily growing larger, their icy grip on the planet's poles strengthening. Sea levels, which had been rising steadily, threatening coastal cities and displacing millions, have stabilized and begun to recede. The extreme weather events that had become increasingly common, hurricanes, droughts, floods, are less frequent and less severe, a testament to the planet's newfound equilibrium. The natural world, once reeling from the impacts of human activity, is experiencing a renaissance. Forests, once decimated by deforestation, are regrowing, their canopies teeming with life. Coral reefs, bleached and dying from ocean acidification, are regaining their vibrant colors, their intricate structures once again home to a dazzling array of marine life. The advent of fusion power has ignited a new industrial revolution, built on limitless human ingenuity. Manufacturing is now clean and efficient, powered by fusion's inexhaustible energy. New industries are springing up, creating jobs and driving economic growth. Fusion technology, fueled by cheap energy, has an immense potential to revolutionize almost all aspects of humanity. As we stand on the threshold of this fusion-powered future, it is impossible to fully comprehend the transformative impact it will have on humanity. The challenges we face today, climate change, energy scarcity, poverty, disease, may seem like distant memories to future generations, their lives shaped by the boundless opportunities of a world where energy is no longer a constraint, but a catalyst for progress. Yet, with this newfound power comes a profound responsibility. The same technology that has the potential to solve some of humanity's most pressing problems could also be used for destructive purposes. It is up to us, the inheritors of this remarkable technology, to ensure that fusion's legacy is one of peace, prosperity, and progress for all. The future is not preordained. It is a tapestry woven from the choices we make today. If we can harness the power of fusion wisely, with a spirit of cooperation and a commitment to the common good, then the future is bright indeed. A future where humanity, united by a shared destiny, reaches for the stars, not as distant, unattainable objects, but as stepping stones to a future filled with limitless possibilities. Our journey has taken us from the heart of the sun to the depths of our oceans, exploring the intricate science behind fusion and its transformative possibilities. Fusion holds extraordinary potential to reshape our world, offering a future free from energy scarcity and environmental degradation. It promises a path where energy is a force for unity and progress. The journey will be long and demanding, but the goal is clear. A world where energy is as abundant and clean as the sun itself. The pursuit of fusion power is a profound human responsibility. We owe it to future generations and the millions lacking basic energy services. Fusion offers a chance to rewrite human progress, breaking cycles of scarcity and conflict. This opportunity comes with an obligation to use it wisely and equitably. Fusion must be a catalyst for global cooperation, transcending boundaries. The decisions we make today will shape humanity's future. Imagine a world where every child has access to clean water, nutritious food and quality education, hospitals powered by inexhaustible energy, life-saving treatments for all, cities as engines of innovation, with fusion reactors gracing their skylines, streets alive with the quiet hum of electric vehicles. This is the future fusion makes possible, where energy scarcity fades away, a future where humanity tackles its most enduring challenges, exploring the cosmos and unlocking human potential. The path to this future is clear but requires commitment. Embrace bold ideas and human ingenuity. Fusion power is about building a better world, a world where our children inherit a future filled with hope. The journey towards a fusion-powered future is worth taking. It will test our limits and inspire our dreams. Let us embark on this journey together, for in fusion we find a reflection of our boundless potential. Disclaimer: this video is for educational purposes only and is not professional, scientific, medical, legal or financial advice. Always consult qualified experts. Use this information at your own risk.